Hi guys, this is Peter and I'm making a video to discuss the exam preparation past paper, the Eastern Cape prelim paper of 2015. Let's get started. Okay, only one student submitted and this is comments on student attempts, so I'll only give a feedback to that. Okay, 4 possible options are provided. You have to choose the best one to answer it. Oh wait, this is paper 2. Okay, there we go. So the front of a modern car is designed to crumple in case of head-on collision. The chance of serious injury to the passenger is reduced since because and then they give us 4 options. The net force acting on the passenger is reduced since the contact time for the car to stop decreases. Now, if contact time decreases, this is where we should remember the formula for net force during the case of a collision is that F net is equal to change in momentum, because when we do collisions we're working with momentum over change in time, and so they're telling us that this decreased in the first question. Now, if in a fraction the denominator decreases, the whole expression will increase, so that's not true. The net force during is reduced since the rate of change in momentum decreased. In other words, rate of change in momentum is exactly this thing. Okay, this is called the rate of change in momentum because this is the change of momentum. The moment I divide with time, it's rate of change. Okay, so just that is change. If I divide that with change in time, it is the rate of change. Okay, then it becomes the rate of change. Okay, so B is the correct answer. Okay, you'll see this one, net force acting since the change in momentum is reduced. Okay, the net force is reduced since the change in momentum is reduced. Okay, so the reason why the change in momentum is not reduced is because in an accident, yes, if I could change the change in momentum, that would have an effect, but it's impossible if a car, the only way to stop the change in momentum is to stop the initial velocity, or is to decrease the initial velocity, because the final velocity is still 0. So the only way to decrease the change in momentum is that the car has to drive slower, and that's not what we're talking about here. We're talking about the crumpling zone. What the crumpling zone does is it extends the time to stop. So it doesn't change the momentum, it changes the time. Net force since the change in momentum is decreased. So no, the change in momentum is not decreased, nor is the change in momentum reduced. No. No, that's the only valid answer, B, so well done to student 1. An astronaut has a weight of W on Earth. He lands on a plane with mass that's 3 times greater than Earth and a radius twice that of Earth. What is the weight of the astronaut on this planet? Take the radius of the Earth as r. Okay, so if we had to do this one, on Earth he has a weight of W. Now, on a different planet that has 3 times the mass of Earth, though the thing that you'll have to keep in mind is that the gravitational constant is equal to the mass of the planet. The mass of the planet, gravitational constant divided by the radius squared. Okay, so now what happens is that the double we get is now weight is equal to mass times gravity. And then, so mass is just multiplied there. Now we're talking about this part. The mass is 3 times as much. So the weight will be also multiplied just with a 3. But now the radius is twice as big. And so the radius, since we are squaring, would be 2 times that squared, which is 4 divided by 4. So that would be the result, which is 3/4b. Well done to student again. Okay, I don't know the answers, by the way. That's why I work it out. Don't have a memo. 1.3. EP, in other words, potential energy plus kinetic energy at the top is equal to potential energy plus kinetic energy at the bottom when only what are present? Frictional forces, tension forces, applied forces, or gravitational forces. Okay, it's D, only when gravitational forces are present. An object is thrown vertically downwards towards the ground with a height of h, with a velocity v. The object strikes the ground and bounces upwards. It is caught when it reaches the maximum height after the bounce. Which one of the following object versus time graphs represents the motion of the object? Okay, so this is velocity. First of all, we have to notice that the thing is thrown downwards. Okay, so when something is thrown downwards, his velocity increases. So you can see in all of these graphs, my initial velocity is positive. Initial velocity is the velocity I start with. Now, if it's positive, it has to now increase. So because I'm throwing it downwards, it goes faster and faster, faster. So if it starts positive, it must continue positive. Okay, and so it's either one of these two, because both of these are decreasing velocities. So I'm increasing. The next is that the ball bounces and then comes back upwards. So you'll see these graphs aren't beautifully done, but okay. So here it bounces and then it comes back upwards. So this one says that it stops after it has some sort of velocity. You'll see immediately when it comes back up, it has a negative velocity because downwards is positive. So here it reaches the ground, then immediately it bounces back up with a negative velocity that's more or less the same as the velocity it reached the ground with. Okay, then it goes back up. Here it stops at 0 velocity. Here it stops at some positive velocity. Now the trick is it says the ball is caught when it reaches the maximum height after the bounce. Now maximum height is when my velocity is 0. So that's there. Okay, if my velocity is not 0, then the ball is still going upwards or is busy falling downwards. But when maximum height is velocity 0. So answer is A. Well done, student. An astronomer obtained the following spectrum of lines of an element. The spectrum of the element in the laboratory and the spectrum of the element from distant stars. The observation confirms that so this is the observation this is the observation of the element in the laboratory. The same element in distant stars appears like this. So notice what is happening here. First, you need to understand the difference between blue and red is that red has longer wavelengths. Okay, so in other words, the spectrum that we're observing here is 2 blue lines and a red line. Now this is important to understand that red has longer wavelengths, because what we're seeing here is that all of the observations are more towards the longer end of wavelengths. Okay. Now what that means is that the wavelength I'm observing is stretched out. And that is because the star is moving away from us. This is the Doppler effect. When something is moving away from me, the observation is the wavelengths are stretched out in a sense. Okay, so the star is moving closer to Earth. No. The Earth is moving towards the star. No. The temperature of the Earth is decreasing. No. Or the universe is expanding. This is evidence that the universe is expanding because the star is moving away from us. So obviously the star is fixed in space, okay, just as the Earth. But because of the if I say fixed in space, I don't mean it's not moving. It's just the in terms of distances, we're not moving. Well, this is a hot debate at the moment, actually. But anyways, the universe is expanding. So if you were to put two dots on a, just to explain, if this was a piece of elastic, oh, and this thing's giving me trouble. Sorry, guys. If this is a piece of elastic or stretchable cloth or something, and I stretch them out, okay, it's not really that the dots are moving, but relative to each other, because the fabric is expanding, that's why they look like they're moving. That's basically what I mean. Okay, so let's go to the next one. So that is D. You should see how student 1 did. Okay, 1.5 D, well done, student. Okay, 1.6. A stationary truck sounds a siren of frequency F0. A girl walks at a constant velocity towards the truck. She passes the truck and then walks away from it. Which graph shows the changes in the frequency heard by the girl over the distance that she covers? Okay, so she passes the truck, then walks, which one? Okay, so initially she's walking towards the truck, which should be, well, a siren at frequency, a stationary truck. Okay, so it's very unlikely that she heard any significant difference. But anyway, as she's walking, the one thing you need to understand is that she is walking at a constant velocity. If her velocity was increasing or decreasing, then in other words, she was accelerating, then there would have been maybe slanted lines. But she's working at a constant velocity towards the truck. That's important. So her frequency observed initially is constant, not like this. She's not hearing. Yes, the noise is becoming louder because she's getting closer, but frequency has nothing to do with this loudness of the sound. It's got to do with the pitch of the sound. Okay, so now if we, so it's constant. So is it more or less than when she stopped? She passes the truck and then walks away from it. So there's a little time when she is basically at the truck and then walks away from it. So is it initially more or initially less? When I walk towards something, okay, it is as if the observed frequencies are squeezed together because I'm hearing them following closer because I have velocity myself. And so it is a higher velocity and then a lower. So the answer is A. Question 1.7. Two spheres A and B have charges of +1 and +2 respectively. They are brought in contact with each other and then move to their original positions. Okay, so both of them have positive charges. The new charge will be the average between the two. So the amount of charges that is transferred, that's now very important. Okay, the new charge will both be a half. Okay, 1.5. But charge C doesn't give 1.5 charges to C, nor does C give 1.5 to, nor does B give 1.5 to A. Sorry. What happens is that the new charge is a 1.5. So how can this one get 1.5? He needs 0.5. So B is going to give 0.5 to A. So the answer is A. 1.7 is Okay, so this one is wrong. 1.7 from B, 0.5 from B to A, because B has more positive charges. Actually, I think I understand why the students said answer B, because what is transferred is actually electrons. And so obviously A has, both of them have a deficiency of electrons, but B have a greater deficiency. So A would give negative 5 coulombs charge to that one. Okay, but that would have to have shown here the negative. So negative 5C from A to B, that would have been correct. If A gave a negative 0.5 charges, and that is technically what happens, I would agree with the student, but the net effect is that if we just talk about the charge transferred, not the electrons transferred. So yes, if I transfer one electron from myself to someone, I have transferred a negative electrons, but that person has transferred charge to me because he's transferred positive charge to me. So we'll have to look at that, and in that case it would have been A. 1.8. A simplified diagram is shown below. There it is. A coil, the ABCD coil rotates. Okay, so first we have to figure out what type of it's a generator. So for generators, we use the right hand rule. Okay, so I use my right hand to put my palm facing north to south. So my palm is facing north to south, and then my thumb then must point in the direction of the current, which is from A to B. So if my right hand from north to south, and my thumb from A to B, and then my palm is facing downwards, which means that in this case my palm shows the direction of the push. So I'm pushing downwards on here, which means this is going anti-clockwise, which is anti-clockwise in here. And then let's just see anti-clockwise, and then it's asking, then reverses its direction, reaches the vertical position, reaches the vertical, and then reverses. So anti-clockwise, either B or D, and then reverses its position. Just trying to, this is a generator, so it generates current. But no, this thing isn't rotating by any force. It is rotated. It's rotated by an applied force. And so in a generator, we won't change the direction of the generator. We'll continue to turn it in a clockwise direction. What will happen is once it passes the vertical position, yes, then the current will change. So this is just an alternating current circuit because there's no slip ring in there. But no, it wouldn't change. We wouldn't actually change the direction of the motor. Unless they tell us that this is somehow an alternating current motor or a direct current motor, I don't know. But no, this one is just B. Okay. So that's question 1.8a. This is A. I am fairly certain it is B, anti-clockwise. Okay, in that direction, using the right hand rule for generators. For motors, we'll use the left hand rule. Okay, question 1.9. The circuit below diagram consisting 3 resistors and a battery is an EMF of 12 volt, an unknown resistor R, internal resistance. Okay, the switch is closed. Okay, so the switch is closed. So initially just notice that where the switch is in an open branch, okay, or in a parallel branch. So when the switch is open, there's still a current, okay, and R1 and R3 is in series with one another because the total current is passing through R3 because it can't split up. There's no way to go in that way, and the total going, so they're in series with each other. So now when it is closed, what will happen to the ammeter? First of all, the moment that you close it, you are adding these two in parallel to each other. Now what that basically does is it reduces the resistance of R3, because now any electron coming here has an option. Do I want to go this way or that way? Okay, so since there's two options, there's two paths to take. It's like opening having doors, and a lot of people trying to stream into one door. The moment you open another door, yes, there's still resistance. Everyone can't go at once, but there's now at least two doors. So once you put something in parallel with each other, you reduce resistance. The moment you reduce resistance and current has an inverse relationship, so you increase the current. More currents can pass, electrons can pass by a certain point now because the resistance is reduced. So what happens to the external resistance? The external resistance is increased, okay, decreased. So A, B, or C. What happens to the ammeter reading? It obviously increases. Okay, so A. 1.2, a neon lights up when a large external voltage is applied across it. Which one of the following best describes the type of spectrum when observed when a gas inside a tube is observed through a diffraction grating? Okay, so let's quickly talk through each one of these. So an absorption spectrum would be the specifically when white light is shown off on a certain color or surface, and then the light that is then reflected has observed certain other wavelengths, and so it will produce a spectrum of light, and some areas of that spectrum would be absorbed. Continuous emission spectrum is what we observe when we observe white light. It produces that rainbow color of effects. A line absorption spectrum, okay, that's when, for example, there's a certain element in the atmosphere, and as light shines through that atmosphere, the light that comes out on the other side, some lines of the spectrum have been absorbed, specific wavelengths, because of certain elements that appear in the atmosphere, and that would also be light that has been taken away. But when we shine through a voltage through fluorescent light, for example, or a neon light tube, the neon itself releases a photon with a certain amount of energy, and as a result a certain frequency. That frequency is observed with our eyes as a certain color, and so this is line emission spectrum. It doesn't produce a spectrum of light, a continuous spectrum of light, rather just one line on that spectrum because of the energy that specific photon has. So that's the line emission spectrum that we will observe. So 1.10 is D. Again, well done, student. That is our short questions. Following is our question 1, which is Newton's law question.